Okay, so our next speaker is Snyder from Indiana University, and he's going to tell us about local topological field theories with values in Morita categories. And there should be no alarms during this talk.
Hopefully. All right. Well, thanks so much to the organizers for the invitation. I'm always very excited to come to Scotland, and my pitch from this trip is that the Isle of Harris comes highly recommended if you're looking for Scottish islands. Anyways, I changed my title ever so slightly to make it a little bit different from Claudia's title. I want to talk about n plus k dualizability in Morita categories of en algebras. So the point here is that in her talk, she talked about n-dualizability of en algebras, and I want to talk about like n plus 1 dualizability and n plus 2 dualizability. This is going to be, to the extent that the stuff of this that is my work is joint with some of it with Chris Douglas and Christian Pries, and some with Adrian Brochier and David Jordan. I should say the perspective that I'm giving on it will sort of shortchange. You won't see as much of this. And we had maybe some slightly different concerns in this. So if you just sort of count like which theorems are where in this particular talk, it won't give you quite the right picture of the balance between those two. But great. Okay, so let me recall a couple things that were mentioned in Claudia's talk. So a d-dimensional local or fully extended TFT is a functor f from some d-dimensional bordism category, which goes all the way down to points. So the objects are points, the one morphisms are one-dimensional bordisms, put corners around, to some thing I'm going to call T for target, which is a symmetric monoidal infinity D category. Okay, so it sends points to objects, it sends bordisms to one morphisms, etc., and does so in such a way where gluing on the bordism side matches up with composition on that side, and the disjoint union matches up with some tensor product over on this side. These comes in flavors. I'll try not to go too low, but I'm not quite tall enough for this blackboard. Despite only being 1 inch shorter than the average person. Math spaces are not always built for the average person. But anyway, so this comes in flavors like oriented, spin, framed, etc. That just depends on what bordism category you're putting here. So this should be refreshed from before. So what I want to remind you is, what targets are we talking about? Targets. And these are going to be these Morita categories. Maybe call alg and unpointed.
Is that a hybrid word, or I like the word?
What word?
Morita.
No. Morita categories, great. I got myself confused about whether I was going to put unpointed in the notation, and the id moved earlier. Okay, so here W is for world. It's the world that we're working in. Is some symmetric. It's some symmetric monoidal K, or maybe infinity K category. And so that's where the n plus k is coming from. We're looking at en algebras in some k category, and that's giving us n plus k levels total. So the objects here are en algebras. The morphisms are en minus 1 bimodules. So they are simultaneously an en-1 algebra with compatible actions of en algebras on them, etc., down to E0 bimodules. But this is actually kind of a lie because I want unpointed ones. So there's a very weird thing that I don't have a deep conceptual explanation for, but somehow in algebra and representation theory, we study unidal algebras, but unpointed bimodules. And this is weird, but it's what we do, and it's what we're going to do here. So at all of these levels, I do want units, but at this level, I don't want a unit. If you put in some kind of pointing there, as we saw in Claudius' talk, you have no hope of getting dualizability past level n, so it's important that I take the unpointed thing here. Okay, so that's the first n levels, but then I want levels above that, which are some kind of bimodule maps. They're morphisms in my K category, together with some compatibility with the bimodule structures. And then bimodule 2 morphisms, all the way up to bimodule K morphisms. Okay, right? So that's going to be our example. This exists by combining work of Haugseng with work of Claudia and Theo's. The rough idea is, so in order to get this part with unpointed, you have to use Haugseng's work, and then this lets you put on this top bit and does so in a way that can work with different kinds of inputs at the first bunch of levels. Yes?
Can I ask you, any examples? What, like we sort of spent a long time with Claudia on kind of lax and off-lax bimodule maps?
Yeah. Great point. I want all of these to be strong. Great. Yeah. Other questions, comments, concerns? Okay, so this is what we're going to work in. W is going to vary a little bit. Great. Okay, and the last thing I need to remind you of is the bordism hypothesis. I think in Claudia's talk, she gave a more detailed description of all the names to put, but I'm going to put Lurie, etc. for now. And the first part of it, I think I'm not actually going to get to the second part of it, so I'll only write the first part today. Local framed, and it's important that they're framed, TFTs in some target T. These form an infinity groupoid because the objects are functors, so there are maps between them given by natural transformations, etc., etc., etc. They happen to all be invertible, so this forms an infinity groupoid, which is a space. And the claim is that this is equivalent to another space, which is the core of take the target and take the fully dualizable part of it. Unlike in Claudia's talk, I am going to have to tell you the definition of what fully dualizable means. Core here just means throw out the non-invertible maps. So on this side, it happens there are only invertible maps. On this side, they're non-invertible maps. You just throw them out. And the map in one direction is clear. It sends f to the value of f on the positively framed thing. So framing is a trivialization of the tangent bundle. And for technical reasons, you should, in lower dimensions, you should thicken things up into the top dimension and frame that. So framing on a point, you take the point, you thicken it up until it's n dimensions, and you frame that. So there are two framings on the point, a positive one and a negative one, and you see where the positively framed point goes to. It goes to some object. That's the map in that direction. And the claim is that's a homotopy equivalence. Now, I only gave the map in this direction. This is unfortunately not really the useful direction if you care about doing calculations or constructions. and I think this is maybe some of, you know, this factorization homology approach should help with those kinds of questions. What we really want to do is go the other way, start with some fully dualizable object over here, and get some TFT out of it that we can actually calculate with, but that's not sort of the direction that this goes in. Nonetheless, what we're going to do is forge ahead, and for a particular target, try to figure out what the fully dualizable objects are. That tells us what the TFTs are. We then have to do a bunch of work to see what they actually look like and what we can use them for. And Adrian's talked a lot about things one can use this for and things we hope to use it for in the future. And so I'm really not going to talk much about what you actually do once you get the TFT. I'm just going to say, what do we know about fully dualizable objects? Hopefully you can then calculate something from it. Hopefully you can then apply it, but this talk isn't going to concentrate on that aspect. Okay? All right, so I need to tell you what fully dualizable is, and I'm going to do that in a slightly funny way, which I do kind of think is the right way to think about it. So I'll give a little pitch for why I think this is the right way to think about this. So given some target, if you have, and probably this is horrible notation, suppose I have some sub-infinity n category, by which I mean like I take some of the objects and some of the morphisms and some of the two morphisms in a way that's still closed under tensor product and composition. Okay, so this isn't like a whole subcategory or anything. It's just I want to say that this subcategory is R-dualizable if a bunch of things happen. Every object has a dual, and I'm actually going to write this down once. So this says that you have a co-evaluation map from 1 to x tensor x dual. This is co-evaluation. You have an evaluation map from x dual tensor x to 1, and they satisfy some zigzag relations. I'm going to drop the tensor products here just to, there should be, you can take x maps to here by doing the co-evaluation on the first spot, and then you do the evaluation on the second spot, and that should be the same as the identity. That is to say, there should be some two-morphism that's an equivalence, a two-morphism with an inverse making this work, and it's the same thing for x dual. And that's what it means for a thing to have a dual. Okay? Now, one important thing about this is it only made reference to objects, one-morphisms, and equivalences between one-morphisms. So it only takes place it doesn't, the question of whether an object has a dual is only a question about a two-category of objects, one-morphisms, and sorry, I'm not counting to 2 correctly. And invertible two-morphisms, but that's an infinity 1. Well, anyway, it doesn't, yeah, okay. That's right, I forgot the tensor. Yeah, the tensor product is sort of -1. Yeah, let me come back to what I just said in a moment, and it'll make more sense. And then I want to say every one morphism has a left and right adjoint. And the way this works is if I have a map from A to B, which I'm going to write as a bimodule because that's what my examples are, it's going to have a left adjoint and a right adjoint, which are some expressions like this. They go back the other way. There's both a left one and a right one, but the things that they satisfy look just like this, except instead of tensor product, I compose them, okay? And now you see why there are 2 levels. There's the objects here, there's the one morphisms, there's the zigzags, and then I only care about equivalences of zigzags. Okay. And the important thing is just that there are now two of them, but otherwise it's the same. And then I keep going all the way to R-1 morphisms. And you don't look at R morphisms because really, remember, all of this involves some layer plus the next layer. And so you want to still have a next layer around. So you stop at R-1. And that's what it means to be R-dualizable. Okay? And the fully dualizable part is the maximal d-dualizable subcategory. So you start with your category and you start throwing out things that don't have duals and adjoints until you end up with something where everything does have duals and adjoints, and it's kind of the largest one. This definition is not actually going to be important for this talk, because what I'm always going to do is tell you some subcategory that is itself dualizable to some level. Okay? I'm never going to say these are all the dualizable things. I'm just going to tell you dualizable subcategory. And hopefully by the end of the talk, you'll sort of see why that's a good technique. But I should also advertise that it's knowing that you have a dualizable subcategory is also useful from the TQFT point of view, because you know what the dualizable maps between them are, and that tells you information about defect lines and stuff like that. So it's actually better to know some subcategory that is dualizable enough. And I'm not usually going to say fully dualizable. I'm usually going to tell you this number here. And the reason I'm going to tell you this number is that suppose I have like a 4 category, an infinity 4 category. I could just think of it as an infinity 3 category by throwing out the non-invertible maps at that top level. And so I'm often going to fix this n plus k category, but I might, maybe k will be 2, so I have like an n plus 2 category. I'm going to tell you what do I know about n-dualizability, what do I know about n plus 1 dualizability, what do I know about n plus 2 dualizability. Those are full dualizability in those modified versions of the categories where I've thrown out the non-invertible maps. So because I'm often going to take a fixed category and shift perspective a little bit like that, I'm going to actually write down the R and never use the words fully dualizable, because you won't know which of those contexts I'm in. Okay. All right. Are people okay with the setup here? All right. And I want to emphasize one thing. From my point of view, higher categories are very hard. I know different people have different opinions. I want to make the point that the extent to which you have to think about genuinely higher category theory is very restricted. In order to apply the cobordism hypothesis, you need to know you have an infinity n category, or an infinity n plus k category, which you get from this. But in order to check full dualizability, all you need to know is statements about a bunch of 2 categories. And 2 categories are not so scary. Okay? So, so once someone has told you that they really fit together, then you can go and just think about 2 categories, and so nothing scary ever happens in the actual calculations of dualizability. Okay? So in particular, when you're checking dualizability, you don't have to worry about issues like which model of infinity n categories are you working in, any of that kind of a thing, because everything is just bicategories, and bicategories are well understood. Okay? All right. So let me start with a warm-up to just remind you what's going on with dualizability beyond n. So our warm-up is just going to be W is that, and n is 1. So we're looking at, so here we're just looking at algebras, bimodules, and bimodule maps. nothing scary at all going on. And I just want to remind you what duals look like and when things have duals. As we saw in Claudia's talk, A always has a dual, which is A with the opposite multiplication, and the evaluation and co-evaluation maps are just move the action over to one side. Okay, so these are not so bad. But now we want to know about adjoints of bimodules. So we have some bimodule. We want to know when does it have an adjoint bimodule. So the first, there's a little lemma you can prove, which says that if n-dual, which is going to be a BA bimodule, exists, it must be Homs as B modules from M to B, and similarly, n-dual must be Homs as A modules from M to A. Okay, I'm not gonna prove this. It's pretty short, but the point is just that the evaluation morphism lets you think of things in n-dual as functionals on M. So that gives you a map, and then you need to somehow prove that that map is an isomorphism, which is a bit harder, but you can do it. This is like the third of my trips to Edinburgh, where I like spent an afternoon trying to remember how this argument goes because I forget it every year. But anyway, I remembered it at the moment. Okay, so the dual must be Homs like this. And furthermore, for the co-evaluation to exist, so the co-evaluation is now going to be some map, so for example, in one of these cases, it's going to be like a map from A as an AA bimodule to, I shouldn't have written this down because I didn't write down which direction these things go. Yeah, there we go. You want to write down some map like this, and what happens is this has a map to Homs in B from M to M. You can take your function, evaluate it, and then act here, and you'll get a map like this. And what you want this map to be in order for the zigzag to happen is to send an object A to right multiplication, left multiplication. The left multiplication by A commutes with the action of B, and so you need to know that those really live up here and not down there. And what this means is you want to kind of write, if you look where 1 goes, you want to write the identity morphism as a sum like this. And that's like writing the identity in a vector space as a sum of E lower I, E upper I. You need some dual bases. When do you have dual bases like this? What's exactly when M as a B module is projective. Okay. So the things I want you to take from this is that the dual in bimodule categories always looks like some kind of Hom. Yeah.
But don't you also want finite degenerated?
Yes. Yeah, so there's this word which usually means like finitely presented or finitely generated, and the category theory word is compact, but they need to be projective and they need to be kind of finite. Yeah. Okay, so what I want you to take from this is that the duals look like Hom categories, and that, right, so the duals look like some kind of Hom, and there's some interesting things here. So for example, wait, No. Do I need? Yeah. Okay. Remark, this only depends on one action. My condition for M to have a dual on one side only involve one action, and to have a dual on the other side only involve the other one. You can actually see a proof of this in quite a lot of generality in higher algebra. So this is a very general phenomenon that this dualizability only depends on what's going on one side, but that's a nice thing to know. Great. Okay, so what happens if you want things to be two dualizable? You want them to be dualizable one more level. Well, you need to know, so for A to be two dualizable, so we just said what it meant for them to be one dualizable. What does it mean for them to be, oh, and did I make an off by one error in my definition? Okay, all right. No, good, okay, yeah. Okay, A is two dualizable tells you that A as an A tensor A opposite module is projective. Because in order for it to be two dualizable, it has to live in a category that has its own evaluation and it has to live in a subcategory that has evaluation and co-evaluation, and those need to have adjoints. Okay, so that means A as an A tensor A opposite needs to be projective, and that A as a K module has to be projective, and these two things are the same thing as saying A is separable, which is a classical notion about algebras, which combines semi-simplicity with separability in the sense of field extensions. Okay, so it's slightly stronger than semi-simplicity. It's the same as semi-simplicity if you're working over the complex numbers. Okay, so this is like a semi-simplicity assumption. And once you know that an algebra is separable, yeah.
Sorry to be about that, but
yeah.
doesn't need to be finite dimensional.
Doesn't separable include that?
I don't know.
I think separable actually includes that. This is one of these things about like ring theorist's definition of semi-simple actually says finitely semi-simple usually. Anyway,
I also like separability comes from the
Yeah,
as A tensor A. Like you don't do also need it to be finitely generated as kind
yeah.
of
Okay.
And it coincides with semi-simple actually over any separably closed field.
Yeah.
When you say projective, we should just take it that you mean compact projective.
Yeah.
Every time, yes. And these arrows are if and only if, or
Let's see. This one is not obviously an if and only if. I think this one is an if and only if, but it's not going to matter because it'll circle back on itself at the end. And then the interesting thing is once an algebra is separable, all the, I should probably say finite dimensional or finitely generated, all the finitely generated modules over it are automatically projective. Okay? Because, like once a ring is semi-simple in the sense that that it's semi-simple as a module over itself, everything is semi-simple, right? So it says all finite dimensional modules are finitely generated, maybe I want to say, are projective. And so that tells you that you have a huge collection of bimodules over these things that all have adjoints. And so what you do is you look at alg2sep, where the objects are separable algebras, finite dimensional separable algebras. The one morphisms are finite dimensional bimodules, which are automatically all projective and hence automatically all have adjoints and bimodules. So this is our candidate for a fully dualizable subcategory. Okay? And we need to be a little bit careful that this really is a tensor subcategory. For example, you need to know that if you take the tensor product of two separable algebras, that it's again separable. You know that if you take the tensor product of finite dimensional bimodules over something finite dimensional, it's again closed. But once you know that it's closed, you can check all this stuff here. Okay, so this is all well-known stuff that's supposed to be sort of easy, but it gives you a parallel for everything that we're going to do in the future. We start with a collection of things. Only some of them have adjoints. We kind of guess a good category of it that we hope is going to have the dualizability properties. We need to check that you really do have the adjoints, and you need to check closure. Okay? And I want to make one more remark before I leave this. Finite dimensional C-star algebra is enough. So one way to guarantee that you're a separable algebra is to be finite dimensional C-star algebra. So you could have instead guessed, let's look at finite dimensional C-star algebra as finite dimensional bimodules, maybe with some compatibility with the inner product between them and bimodule maps. Okay. That's all I want to say about that. That's the end of kind of the background. Now we're going to dive into the real results that I want to talk about. So are there any questions about this before I move on?
Just a remark, you
Yeah.
said it out loud, but this circles back, and so everything is different only now.
Yeah, that's right. Yeah, that's right. So in this case, we do really see that this is the whole fully dualizable subcategory, but that won't be the case for any of my future theorems. All right, so now we're going to take W to be a two-category of categories. So this means alg 1 of W is going to be some kind of monoidal categories together with bimodule categories, bimodule functors, and bimodule natural transformations. And L2 of W is going to be something that has as objects braided monoidal categories. And then some stuff here that you have to be a bit careful to get exactly what the right definitions are. But these are the kinds of worlds that we're working in. But at this point, there's kind of a very dangerous category, a very dangerous question, which is what kind of categories are we looking at? So we have to answer the following questions. What kind of categories? What kinds of functors? And the question that really brings home that maybe you really need to be careful here. What tensor product on categories? For no particular reason, I'll use square tensor product for tensor product of categories. Anyway, but it's traditional. Great. And it's always, I always get to a point in talks where I'm like tempted to be like, here's this big confusing mess. And I'm like going to really break it down and explain it to you. And I think it never really works. I think instead what you can just do is warn people about the general shape of the confusion. And so that's what I'm going to try to do here, is tell you not how to get unconfused, but like what things you should expect to be confused about. There's a question. Yeah.
Well, I mean, maybe you'll disagree, maybe you'll explain something like this, but I would have thought that like the tensor product should be the representing object for bilinear things. So I would have thought that once I decided to answer to question 2, I would have known the answer to question 3.
Sure, that's a very reasonable point of view. Yes.
But also you have to show that it exists. It will universal property.
Yeah, that's right. Yeah. So this should be have some universal property for bifunctors coming from this level. So once you have this level, you know what this should be. You don't know whether it exists or not. Yeah. Okay. So, warning. So then here comes the warning. So there are kind of three kinds of places you might work. There's something over here which you might call the Cauchy world, or the tiny world, or the naive world, where you just work with, like, everything is going to be k-linear for some field for me, so I'm not going to write that every time. But in this world, you're looking at sort of just additive, idempotent complete categories. So it's just like, and this is a pretty big world, because if you take any category, you can take its additive closure and its idempotent closure. And so what I mean by this is you can take direct sums, and you can take kernels and images of projections from a map from an object to itself. Okay.
So what does it have to do with Cauchy?
That's a great question, to which there's an extremely long answer at the end lab, which I could not possibly give you. But basically, there's a way that you can think of metric spaces as categories enriched in numbers instead of sets. And if you take that point of view, somehow additive and idempotent complete matches up with Cauchy complete in a way that I don't understand. But I like Cauchy as a word here, because I feel like calling it, for a long time I've called it naive, and I feel like that's insulting. And so I've shifted to Cauchy, but
Maybe it's insulting to Cauchy.
yeah. So this is additive idempotent complete with kind of a very boring tensor product. You just like make the objects in the tensor product be like pairs, an object here and an object here, and then you Cauchy complete that. You take the idempotent and additive completion of that, and you get something. And it just always works, and there's nothing hard happening. It just works and it's nice. Okay? Yeah. Cauchy. I also want to give you some indication of like where you're going to find these things. So like in Kevin Walker is always working in this world. Okay. Now there's another world over here, which I'm going to need a little more space for, which I'm going to call the small world. There are a bunch of different things. So the important things about the small world is that things should have some finitely co-complete or abelian-likeness, and your functors should be right exact. Okay, so you want right exact functors. That's the really important thing. Is that you want right exact functors, and you should have finite colimits. Okay? So this is sometimes called rex. For right exact, it is categories that have all finite colimits and right exact functors for them, and the tensor product in this setting is often called the Dolan tensor product, or Kelly sometimes.
Choose that t-shirt because for a while we want to call the category of tensor category the T-Rex?
Yeah, that's right. A tensor category in Rex is a T-Rex. And this is not a T-Rex because this is a Canadian t-shirt, and it's like whatever. They change the name of Albertosaurus? Anyway, but if you ever go to Banff, there's a very good dinosaur museum in the middle of nowhere, an hour and a half from Banff, and that's where I got this t-shirt. Great. So the reason I wanted to leave a little bit more space is that there are a bunch of other settings that are kind of contained inside this world. So for example, finite categories in the sense of the tensor categories book. These are ones that are equivalent to the category of finite dimensional representations of a finite dimensional algebra. Locally finite categories. Abelian categories with length. this is the generality in which Dolan works. So locally, so finite category, I gave you one definition. There's another that's like you have enough projectives and only finitely many isomorphism classes of indecomposable projectives. Here you drop that latter condition, and here you drop even there being enough projectives. You just know that objects have finite lengths and Hom spaces are finite dimensional. Okay, and the typical
No. In the book, if you say locally finite, in the tensor category book, locally finite is the same as a abelian with finite length.
Oh, really? Okay.
Yes, so you drop both conditions.
Oh, okay. All right, great. Okay. Great. So all of these, everything in the EGNO book works in this kind of Rex world, although with additional restrictions. Okay. And your typical example here is finite dimensional vector spaces. And if you look at like things like fusion categories, you're only allowed finite direct sums. You're looking at things that are, and then down here, there's the big world, where you use something called LFP, locally finitely presentable categories, which are co-complete, and so you could actually ask for co-continuous functors.
Or maybe you drop the F.
What?
Or maybe you drop the F.
Maybe I dropped that.
No, bro, you don't.
Okay. I don't. All right. So this is the big world. Okay, so that's the first thing. Is there are three worlds you might see? So yeah. So for example, everything in EGNO and that whole realm is taking place here.
Sorry,
yeah.
Whenever you don't drop the L, but you can drop the F.
Okay.
But the small world is doesn't contain the tiny world.
This is a great question. So now let's think about, right, so I want to say a little bit about how these are related to each other because it's not the way you might think. You might think, well, if something has all finite colimits, then in particular it has direct sums and idempotent completion, so I should be able to turn things here into things here. And in particular, right exact functors are functors. Okay, so you might think that you go from here to here. But that doesn't play right with the tensor product. If you take the Rex tensor product of things, it's not the tensor product that you get if you made them naive. So there's not a map this way. But what's surprising is you can go these ways by a co-completion process. So you can go from here to here by something called finite co-completion. You can go down to here by something called free co-completion. And I should point out that, let me put up this name, which I'll do later, but there's this paper by Brandenburg Chirvasitu and Johnson Freyd, which is where I learned all of this stuff, and it's a really lovely, readable paper that will make this clearer. So I want to say you should remember there are three worlds. The relationship between them goes the opposite direction than you might think, and if you want to learn more, that's a good paper to read about it. Yeah.
So if I have two things in the small world and I move them to the tiny world, take the Cauchy product, and then do this co-completion, do I get the mean product?
No. Well, it's the other way. So if you take something in the tiny world, take its Cauchy tensor product, and then co-complete each of them, finitely co-complete each of them, take the Rex tensor product here. That's the finite co-completion of, so the map this direction really does intertwine the tensor products, okay? But it won't hit everything.
So you don't get these things, right? Or
What?
the finite, locally finite categories, you don't get this.
Well, okay, so let me return to that in 1 second. Theo, did you also
I
have a
just
question?
wanted to ask, like,
Yeah.
when you listed sort of subcategories of Rex, you're saying those are monoidal subcategories?
Yes. But not necessarily preserved under relative tensor product when we get in the future. Yeah.
Can
it, I think if I happen to have a small category which has projectives, then I can take
Yes,
the projectives.
that's right.
Right.
Yeah, so what happens is, to get from here to here, you take finite co-completion. To get a candidate for what this comes from, you take the compact projective objects. So the only way this has a hope of being in the image of this is if it's generated by its compact projective objects.
Well, there it's projected.
Yes, because everything is compact. Yeah, that's right. So, yeah. Right. So, these maps go this direction, and they don't hit everything. They only hit things that have certain generation properties. Okay, and this flips things on. Is very confusing for a long time because you talk to Kevin, and he's like, "But there are more of these. Why should I ever look at these other worlds?" But actually, there are less of them because of the things down here, you only see the ones that are generated by their compact projectives in this co-completion. Okay, so they actually, it's really this kind of sits inside this, which sits inside this, not the other way around. Okay, we tend to work here. But the last thing I want to say is there's not a big difference between these two worlds. If you work here, but put the word profunctor instead of functor, you're more or less working here. Okay? And so, and even if you look at the EGNO book, every once in a while they do look at profunctors. And so, so really, you can work in one of these generalities, but you need to put in profunctors to match up with what we do. Okay?
And if you start off with something in this tiny world, but not category of projectives, if anything,
yeah.
Do you get something that you can describe, or do you get a mess?
It's not so bad. It's just like a functor category from the opposite. There's like a UNATA description of what it is, depending upon how much you want to get your hands on it.
Like if you take a tilting category for an algebraic group, do you get something reasonable?
I am halfway through that calculation and can't, I'm very confused about the following question. Take tiltings for SL2, take its finite co-completion, you get something Rex. It somehow maps to both of Victor's abelianizations, and I'm a little confused about what's going on. So I was halfway through talking to a student about this calculation, so ask me in like 6 months and I'll tell you the answer to that question.
I'd say there's a big difference between small and big. And when you say profunctor, you're essentially defining a functor to be, a functor between the big completions.
Yes, that's right. So there's,
the notion of dualizability in small and in big is a large difference.
Yes, and it's better in the large world.
Better meaning less meaningful and more common.
Yes, that's right. Yes, that's right. Yeah, that's right. So, for example, you'll get things in you'll get like infinite dimensional vector spaces instead of finite dimensional vector spaces, which is not as good. Yes, that's 100% true. I think I was making more just the sociological point that if you've grown up on these like I have, you don't have to make the shift necessarily to thinking about these categories instead. You can just make the shift to think about profunctors instead. But you're completely right that dualizability here is better than dualizability here, but dualizability here is more common. Yes. Any other?
Is big tensor product still called Dolan? Or does it have a different name?
Yeah,
I mean, dropped Dolan.
It definitely isn't Dolan. Yeah, I'm a little confused about which I should call Kelly. The Rex version here that's not abelian, or the LFP version. Maybe it's maybe it's clearer. The problem is maybe so that's what we often do is, in a sense, Kelly did kind of both of them, so it's maybe short shrift to Kelly, but we often will use the lean for this one and Kelly for that. Okay. Great. Right, so to be n plus k dualizable in algen, so you have some n algebra, you need the underlying object to be k-dualizable in whatever world you're working in. Okay? And so this is just because, like, when you're taking duals at the lower levels, you're just moving the actions around. And if you do that enough, you'll end up with A with some huge mess acting on one side and just the unit acting on the other side. And that needs to have a dual, which is going to tell you that A has to be dualizable just as an object. So we would like to know what are the one dualizable and two dualizable things in categories. Okay? So, to get one dualizability, and this is again this paper here, it's enough to be generated by compact projectives. And they were unable to work out in Rex whether those were all of the one dualizable things. But if you work in abelian categories with lengths, which is locally finite categories, they actually do prove that these are exactly the ones. Okay, so if you like this, those are exactly the one. But you have to use profunctors.
So this means enough projectives in the language of this book.
Yeah, enough projectives. Yeah, exactly. You need enough projectives, and you need to use profunctors.
That means the evaluation and co-evaluation will be profunctors.
At some level. Right, there's a bunch of levels here now. Yeah. No, sorry, one dualizable. No, so yeah, let's see. So we want that we're just asking. Yeah. Okay. And finite semi-simple categories are two dualizable. This is sort of well known. I don't know who to attribute that to, but if you have a finite semi-simple category, it's going to be two dualizable. And here you can work in any of the worlds. You can work in the tiny world, the big world, the small world. You don't have to use profunctors. It just works. Okay? Great. So now we're going to try to start guessing what we should look at. You need to be a little bit careful because
So these finite semi-simple categories are two dualizable in any characteristic or only characteristic 0?
Any characteristic 0 will come up in a moment, but yeah. So warning.
But no, you can tensor two semi-simple categories and they're not semi-simple if you're over. Isn't there some problem with tensoring?
Relative tensor product. Yeah. So warning, E1 of finite semi-simple categories is not a thing. So in order to define this, not E1, alg 1. In order to define alg 1, you need to know that certain colimits exist to define your tensor products over algebras. And this won't necessarily work because there's this example in characteristic P, you can take vec tensor over vec z mod pz. All of this is in characteristic P with vec, and this is going to be rep of z mod pz. And this is not semi-simple. And so this is a problem. So in characteristic 0, you could say, oh, let's just look at, the finite, look at diffusion categories, but that won't actually be closed, right? So you run into problems not on the dualizability side, but on the closure side.
So you have to consider separable categories.
Right. Yeah. So Right. So and remember, so you have to always kind of balance having duals and having closure. So here, duals look good, but it's not actually a subcategory, so you're out of luck. Okay. So great. So the key idea here is something called rigidity, which is analogous to the C star structure that we saw before. So rigidity is a notion, and rigidity is, I don't feel like a good name for it. It doesn't have to do with deformations. It's about internal duals. So we're studying monoidal categories. We can ask whether inside the monoidal category objects have duals. That's like an involution on objects. It's kind of like a C star structure. Okay? And
well, why is it an involution?
Yeah. Very well. I don't have a good response to that, but yes.
It doesn't have to be.
No.
Does it?
Yeah.
It's only in some homotopy sense.
Yeah, I should not have said involution. Great. Because there's a left dual and a right dual, but okay, so we want to look inside of this. Now, we have to be a little bit careful with how we do this. So remember, with these different worlds, the notion of rigid in EGNO and in most places is something that we call compact rigid, which says that all the compact objects have duals. But there's another notion, which is CP rigid, which only says all the compact projectives have duals. And since the compact projectives are going to generate, because otherwise we have no hope of getting n-dualizability at all, this is often good enough. And CP rigid has better closure properties. And I want to say that this was explained to me by Theo, and it's why I understand this stuff. But so, for example, if you take tensor products of rigid categories and characteristic P, they might not be rigid, but they will be CP rigid. If you look at the category of AA bimodules for some non-semi-simple algebra A, it won't be rigid, but it will be CP rigid. This comes in like when I first was talking about this stuff with Chris and Chris, I have lots of people want to know, can you get some if and only if? And one of the problems was that AA bimodules is definitely dualizable, but wasn't rigid in the sense that we were using it at the time, but it's rigid in the CP rigid sense. So this notion of CP rigid works in a lot of cases. Okay.
Maybe it's worth mentioning QC on an algebraic variety. If the variety is smooth, it's CP rigid, but not rigid.
Yeah, that's right. So yeah, there are lots of examples. Yeah, basically any example coming from algebraic geometry will never be compact rigid, but may well be CP rigid.
But so do you have some analog of this theory of Frobenius-Perron dimension for such categories?
That I haven't thought about. Yeah,
because that's a kind of, I would think, a main sticking point of getting some definitive results about it.
Well, I mean, some of these might even be infinite, and so of course there's not going to be.
No, but for the finite case.
Yeah. Let me just. I want to end by giving you sort of the table of what we can get from this, and so the interesting thing is that CP rigid is going to have both good closure properties and is going to guarantee dualizability. So I'm just going to finish, because I'm out of time, with just a chart of kind of the results that we can get from this. So remember, we could ask, is it 1 dualizable? Is it 2 dualizable? Is it 3 dualizable? Is it 4 dualizable? For each of E1 and E2 in LFP. And what we get is, of course, from Claudia's talk, I can fill in always here. here, what we want is CP rigid and generated by compact projectives. Here we want CP rigid and generated by compact projectives. It's a little surprising that that CP rigid is enough to give you both this and that. If you look at other characterizations, say like smooth and proper or something like that, that tell you all the fully dualizable things, you're going to need more conditions down here than here. But CP rigid is enough to guarantee both of these. And then finally, down here, what you get is multi-fusion categories with global dimension not 0. And these are called separable tensor categories, and they get rid of this problem. And here you get braided multi-fusion. This doesn't make sense. Great. Okay.
With dimension not 0, yeah?
Yeah. Dimension non-zero.
Are these if and only? So these are
None of these are if and only ifs. All of them are sufficient. Yeah. No, yeah. The always are necessarily insufficient. The rest are just sufficient. All right, and that's it.
What if,
Are there any questions for us?
We have example of like four-dimensional non-topological categories. So that seems to contradict the statement. Am I confused by something or?
Let's talk about this afterwards. I may be confused.
certainly very helpful.
Yeah, it's certainly helpful if they are, but I thought. Yeah, let's think about that afterwards. I'm not going to answer it.
I thought that so even this four-dualizable thing is not or 3 for E1. This is not even only if.
No. So what is true by well, if the paper series got finished, there's this series of papers by Douglas-Schommer, Pries, Victory, and Bartlett. That one of the things that they claim should tell you that the center must be rigid. But if you started with a category that wasn't rigid, even CP rigid, but its center by magic happened to be CP rigid, you'd probably be okay.
So do those exist?
The notion of rigidity is not a Morita invariant.
Yeah.
So you can have monoidal categories which are Morita equivalent to rigid categories.
But CP rigid is better behaved under Morita equivalence than rigid, so I'm not.
But what's
so I don't know counterexamples, but I see no reason why. This is like, are all separable algebras C-star algebras? Probably not.
You can mention a counterexample for the
Yeah.
No, definitely all separable algebras over complex numbers are C-star algebras because they're direct sums of matrices.
But that's an algebra theorem. That's not, it doesn't even make sense over arbitrary fields. I don't know. Maybe you're right. Like, I don't want to say.
No, I understand it might be unknown, but are you sure that it is not definitely?
So what was the counterexample you wanted to
I was
say?
saying at the four-dualizability
Yeah.
level, you can take a non-semi-simple modular tensor category.
Yeah.
And so that in particular, this is Adrian's remark, that's not two-dualizable because it's not semi-simple. It's non-semi-simple as a category. We claim that it's actually invertible. So particularly, it's four-dualizable.
But it's going to have dimension 0 if it is not semi-simple.
I'm not sure what the
I don't-
dimension means.
I don't have any counterexamples that I'm 100% confident on at the moment. But I also see no reason. I think you can take categories whose center is trivial, which aren't rigid, and they may well, I see no reason to expect them to have to be rigid. And the only arguments I know would force the center to be rigid, but there's no reason in general why that would force the thing you're inputting to be rigid that I can see, but maybe I'm missing something.
C3 rigid with enough projective entries, those like you do have to use profunctors. Right?
Yeah, and profunctors.
Okay.
You don't have to use profunctors down here. You need profunctors at